Welcome! Today we're going to examine a critical component of BERT sentence transformers. How good is the cosine similarity approximation if you want to compare two sentences within your body of text? Therefore, we start our Jupyter Lab environment with PyTorch. We import NumPys. We do not need UMAP today, but we need our sentence transformers. We need our transformers from HuggingFace. And I download, of course, Deloitte's Tech Trends 2021, all the sentences within this document, and we will see the number of sentences today is 1782 sentences, and the sentences look like these examples here. Now, since we have with BERT a limited input sequence length, we want to make sure that the amount of words per sentence does not exceed a certain threshold. And we see here with about 35, that sounds about right. And if you want to find a sentence with the most words in it, it is sentence 1169. And those are the words. Okay, so we know we have 36 words. The average is about 10-11 words per sentence. So we should be fine with an BERT input sequence of about 256, I suppose. You are familiar with BERT. You are familiar with BERT sentence transformer. It's gorgeous. They're available now in version 1. And there are different models available, pre-trained models. You see here it starts from about half a gigabyte to 1.24 gigabytes. And we're gonna use a model that's been recommended, paraphrase distilled RoBERTa base version 1. The model is already downloaded, and you notice if you have an NVIDIA graphic card and you have CUDA cores, you can of course here activate with this simple piece of code your GPU acceleration for this. SBERT I'm going to use in a second. And now we're gonna encode our model. So we have our sentences, 1700 sentences. We have our model defined. It's a paraphrase trained model. The batch size is 128. We want to show the progress bar. And this is going to take about 20-30 seconds, I suppose. The variables, we want to have a look at the PyTorch tensors. Oh, 52 seconds, longer than I thought. So we just hop on to the next piece of code. And here it now becomes interesting. I choose one sentence from all the sentences within this document. And this one sentence is sentence number 101. And come on, for human, this sentence would be, as human technology engagement continues to increase, the end game is simplicity, transparent and natural interactions. Now, if you apply just the basic English stop words when you're cleaning your data, and these are the stop words from NLTK, you see that typical English stop words are excluded. So our sentence here suddenly becomes the machine translated sentence, human technology engagement continues, increase, end game simplicity, transparent natural interactions. Now, if you ask me, I would not be able to understand the meaning of this sentence if I just see this reduced form here that we use as an input stream to analyze the cosine similarity of these sentences to all the other 1700 sentences that we have within our document. But let's have a look what our artificial intelligence system tells us. We use, of course, here from scikit-learn the cosine similarity. We choose a particular sentence. It's sentence 101. We already defined this. We use the cosine similarity that we just imported of our embeddings, where each and every sentence has a, I guess, 768-dimensional embedding. We cross-reference this with the embeddings of all the other sentences, and we choose number indexed of the sentence 101. We sort the value and we display it. And this is the result that we get. Here is our sentence that we have as a reference sentence. Human technology engagement continues to increase, the end game simplicity, transparent, natural interactions. And now our little artificial intelligence system tells us that this is the next closest sentence. Now, it tries to deduct a meaning, but of course there is no meaning because the machine just takes the embedding of word pieces, the BERT methodology, aggregates all the word pieces to a word if it's not in the BERT vocabulary of 30,000 elements, and then simply adds up different layers, different BERT layers or RoBERTa layers or whatever, SBERT layers, whatever you go with. And you get a presentation of the sentence in a specific embedding. And the embedding is compared, and if you use the cosine-similarity, you see the next sentence would be convenience, simplicity, digital interaction, eventually seamlessly infused, warmth, assurance, meaningful human exchanges. I mean, I could guess what it means without the interpolation, without the stop words, without the comma, without the whatever help we have as human to understand this sentence, but interesting. Notice that here simplicity and simplicity are the words that are identical. Interaction, here we find interaction. Human exchanges, human technology engagement. So you see, it is not like a statistical methodology where you just compare how many words are identical in the sentence. This is really a different methodology. And if you already had a look at our pooling layer when we construct our BERT model, and you know we have an additional pooling layer to get to a fixed length vector of our sentences, you noticed if you use the max pooling sequence, you get a strong cluster depending on the length of the sentence. Because of course, if you pool together all the word pieces of all the different words, and you have, let's say, 4 words, or you have 14 or 15 words, the higher the number you get out of this, of course, it is directly related to the length of the sentence. And it is nice to see here that we have here also included in our top 10 sentences, most similar to our primary target sentence, we have a short sentence with just 4 words. Technology interact, strategic assumptions. Again, as a human, I wouldn't understand because there are some parts missing, generating sense for us. Where's the comma? Is there some reference before the sentence, after the sentence? But we have here, look, what does an artificial intelligence system understands when it reads those sentences and comes up with? So interesting, long sentence, short sentence is within the solution set. That's a good indication. Again here, next most closest sentence cosine to 1 is digital interaction, natural interactions, seamlessly warmth, time expected, digital enhanced, growing number, physical experience, vice versa, data supply chain function, commonly shared, interesting. Do not give too much weight here to, of course, our target sentence has cosine 1. This is identical to our sentence. If he is now 0.56, and why is there such a gap between 1.0 and 0.56? This depends how the embedding is constructed, so don't give too much meaning of this. I will show you in a short time some RoBERTa embeddings where this will be much closer. The relative distance and the relative ranking here is of importance, and you see our artificial intelligence tells us, okay, these are the most top 5 words to our target word. But since we have an embedding, we can deconstruct our own sentence. And I choose here a sentence that's not within the body of all the sentences in our document, but I know that the topic of the document is about low-code applications. So I write low-code applications, and since it's of course a document by Deloitte, you have some thing about change, about business, about transformation. And I've wrote a sentence, low-code application business transformation. What we do now, we calculate, since this is one sentence, there's no BERT input sequence restriction to this, it's short. We have this as our sentence and we calculate the model encoding of our sentence as we've done before with each and every sentence of the document. Then we print out the shape, because there is, if you do some pairwise cosine similarity, you have to watch out for the shape of your tensors that you're operating with. And then we perform again the cosine similarity, the embeddings of the new sentence, to all the other embeddings of the other 1700 sentences. And we just sort the values, and here we go. New sentence is not defined. Well, yes, this is my intelligence. Unbelievable. We have to activate our primary sentence, and here we go. So for the sentence low-code application, business transformation, the closest sentence the system comes up with is business technology evolution function. Sounds interesting. Transforming custom code. This comes now real close. If you have some low-code application and you have the traditional coding system transforming your custom code, this makes sense to me. Company success using low-code agile tandem-led fundamental changes way it operates makes sense, makes absolute sense. There's here low code, and this just shows up in our third sentence here, and the other two sentences have no low code, but the meaning, it's not bad. It's not bad for our little model that we have here, and there's no GPU acceleration, and we use a pre-trained system. So since we have no GPU, it's useless to additionally train a BERT model. The complexity of a BERT model has been trained for hundreds of hours or maybe thousands of hours on the TPU. So we just use the pre-trained model. We download it from the internet, our 1.24 gigabytes of data. But what comes out, this makes sense. This is interesting. But of course, it is heavily dependent on the model that we download. So what we do now is we choose another model. And let's go here, and I say we construct our own model. I already showed this in episode 10 to you. And we have now our sentence transformer. And from HuggingFace, I download RoBERTa large. I have now an extended maximum BERT sequence length for an input of 512. I define two pooling layers. You can also have a feed-forward network that you have a tangent hyperbolicus activation function. But let's stay simple. We just want to understand the basic limitations of the model. We load this model. If you want to have, again, check for the sequence length, it should be 512. And if you want to know the precise model you just designed, no problem. You have here the RoBERTa model. You are operating in 1024 dimensional feature coordinate sets. And I suppose you have 12 layers, 12 RoBERTa layers. No, more. 21? No, 24. Wow, 24 layers. Heaven's sake. This is a complex model. So this is going to take some time. If we encode now our sentences with this model to get the embedding for each and every sentence of our document, I suppose this is going to take 1 or 2 minutes, and I'll be back in a second with you. And now we are back after 3 minutes and 59 seconds. All my 12 threads of my Ryzen 3600 CPU were at 100%. But of course, if you have a NVIDIA graphics card with a CUDA cores, your GPU acceleration should perform this task within 10 to 20 seconds. But it is to show you, you can do it even without a GPU. So just to make sure, we have our 1782 sentences, and each sentence has an embedding in 1024 fictional dimensions. Now, we do again have sentence 101. You notice the stop words for the sentence are the same, but before we do the calculation with this new model, let me just save the result we have from our run before, where we have the paraphrase model. And now we're gonna execute again the same code. We have here our primary target cosine with 1. And now you will see that we have here current calculation, and this is the calculation we have done before, that our first sentence is different. Entire ecosystems connected digital thread increasingly share high-quality data real-time end-to-end. Interesting that this now, with RoBERTa, is our closest sentence calculating the embedding. And the embedding, of course, has been pre-trained on a body of documents. And you have to be really, really careful which model you choose. For example, if you have a scientific text, maybe it's good to choose the scientific version of BERT, or if you have access to a GPU in the cloud or a TPU with Google Cloud, it is really important to pre-train your model on a very specific body of text that are really with high significance for the text you're going to examine. So if you have a look at the other sentences, a lot of opportunity, new solutions deliver realistic, engaging, human-centric experiences. Yeah, makes sense. Yeah, there is some connects to the first one. What is about this sentence? Adds low-code technology coupled recent embrace agile development methodology, surprising impact ability to take new products to market. Yes, sounds reasonable. So you see, because the embedding you use, the model you use, and even the calculation you use, and may I remind you, we have not done any dimensionality reduction. There's no UMAP that we applied. We calculate in the full high-dimensional feature space of the embedding, and we have not any steps in between where we reduce the complexity. This is done with the whole complexity of the system, but you see the result is different. So therefore, be careful which model you use. And we do the same again with the new sentence that I come up with before. We just save our result from the first one, that we have something to compare it with. And let's execute the cell again. And now we have our sentence is low-code applications for business transformation. And we come up with business technology evolution function. Now, interesting, this is the same sentence that the other model came up with. Business technology evolution function. That's interesting. This is sentence number 105, 105. Okay. Then we have sentence 418. The next we have 413. Interesting. It's close. Okay. Next sentence here is embrace low-code technology fueled ongoing digital transformation efforts. Yes, makes absolute sense. Sounds even better. Yeah, it's transforming the old custom code idea. Yeah. Data double team digital transformation. Yeah, sounds interesting. Company success using low kind of way cooperates. 413. 413. Number 3, we have again an identical sentences. Number 3 here, number 5 here. So you see, the model depends heavily on the pre-training. And I would recommend to you, if you're in a specific market, if you're in a specific niche, if you use a specific technology, or there is some books of reference or some documents of reference that are really of importance for you and your future job, your tasks, take them, learn the model on these documents that are important for you. Do not only rely on pre-trained model, or if you have the option, take a pre-trained model, do some transfer learning on this model, include all your documents of reference that are important for you, go on Colab, use some GPU. Colab Plus is unfortunately not available in Europe right now, but find some other solutions. It is, the more sentences you have, I have a document with 300,000 sentences, and you will need about 50 gigabyte of RAM for doing the calculation. So there you have it. This is the cosine similarity for sentences within documents. So if you have a question or a sentence, a reference sentence of importance for you, you want to know within the document which are the sentences that come closest to it. There is an easy effort. You can see the calculation is done in seconds if you use a model not too complex. And you can make sure what is the content in the document. And let's say you have hundreds of documents with thousands and thousands of sentences, and you want to focus in on the most interesting part. And maybe you have not identical keywords like low code. They use another wording for this, so they have another application for this. BERT-based sentence transformer methodology is really an interesting way to navigate around this system and find the sentences that have a closest meaning under parentheses for you. Thank you.